Assalamu alaikum and a very good afternoon to everybody. Welcome to the lecture of electromagnetics. Our course code is BEET 3383. So we start from week 2 because there is one due lecture I need to give. So this is the lecture actually from the last week that I supposed to replace. However, we need to start not directly to electromagnetic principles. We need to learn something very basic about electromagnetism, where we start from learning about some vectors and some coordinate system. And this lecture basically will cover, there are 2 lectures actually, which will cover basically this lecture. We will learn about the vector analysis or vector algebra things, such as the dot products, cross products, and the other things. And the next lecture we will learn about the coordinate systems, and then from those knowledge we will move on to our electric field principle, electric charge and everything, and then from there we will pick up and we will move forward. So this is what is electromagnetic is actually. That electromagnetic is a kind of study where we learn about the principle of electric and magnetic field basically, and knowledge actually we acquire from the fundamental behavior about the fields, how actually it relates with the devices such as resistor, capacitors, relays, transmission line, and everything. However, we will not learn all the devices. We'll basically learn about relays, transmission lines, antennas, waveguides, optical fibers, and lasers, because for the telecommunication engineers we don't concern about the motor transformers that much. Those are another department, basically engineering department, another engineering department. So for us, transmission lines, antennas, waveguides, optical fiber lines, and lasers, how we guide it and what is the effect of electromagnetics on them, we will learn in this course. First and foremost, to electromagnetic theory is actually based on one electromagnetic phenomena which is called as Maxwell's equations. In the beginning it will look a little difficult for you to learn, but however I need to give you a very small sneak peek about the Maxwell equations. At the end of this course you will learn actually how to basically understand and read these equations. But nonetheless we need to learn in the beginning what is this Maxwell's equations are. So there are actually Maxwell equations actually comprise 4 different equations. One equation which is actually from here, the E we see, which is actually determines the electric field. And then how we learn how we can determine the electric field is from B. B is actually magnetic flux density. So if we know the magnetic flux density, then we know what is the electric field intensity. It means we learn about the electric field. Similarly, to learn about the magnetic field intensity, which is H, we need to learn about the current density and the electric flux density. So these all are vectors. Remember, these are not scalar quantities. This current density is a vector quantity, and all of them are actually vector quantity. You can see in this equation there are differentials, partial differential equations. So partial differentials here, and then there's this is called inverted triangle, which is, we call it the DEL operator, means del operator, delta operator, sometimes some people call. We will learn, of course, significant about this, and this is a cross operation between them. So delta and cross product of the electric field. From this electric field, actually, to know about the electric field, we get differential from the magnetic flux density. But however, we will not go so deep here. We will learn this at the end, basically. So the electric field and magnetic field can be determined by this. Now, how we calculate B and D is actually from the electric charge here, the volume charge density, and then the magnetic flux density from here. So in these four equations, combination of the four equations actually have been used by many years to learn and understand how the electromagnetic principle works. So once you become enough knowledgeous about these quantities, E, H, B, D, J, and rho. By the way, this is not P, this is rho. Suffix V means the volume, charge, density. So as long as we know these quantities, it will be easy for us to read all the Maxwell equations. So we move on from here. Today's topic will be basically topic 1, which is vector analysis. Means like we will learn about the vector algebra. So in that this lecture, we will learn about the vector and scalar quantities. What are they actually? The unit vectors, position vectors, vector operations, such as the addition or subtraction, and then the dot and cross product. Most of these topics actually they are well known to you. However, we're just reconnecting back with those things that which is very much have a very huge significance in this course. So due to that fact, we need to go back to those basics and we learn again about them, and then from there you become a little bit confident about how to calculate and how to project and how to think about vector way of electromagnetic projections. Then we go directly to our field analysis. So what is actually vector algebra? Vector algebra basically deals with two different quantities. One quantity is called a scalar quantity, another we call it vector quantity. A vector quantities inherently have a scalar quantity within. Means a vector definitely will have a scalar quantity for sure, but the scalar quantity doesn't have a vector. It means actually that a scalar quantity which doesn't have any direction, it only have absolute value, like the distance, voltage, charge density, and so on and so forth. But a vector quantity which have a value, which is magnitude, and definitely will have a direction for sure. So like velocity, current, electric field, and so on. Sometimes we get confused with speed and velocity. How can speed, because a car have a speed, and then the car also have velocity, even though they are kind of similar quantity, but we represent it differently. The difference actually comes from here. We can check here that let's say you are driving a car that's moving along, and then you are seeing something in your speed meter. We call it speed meter because that meter only gives you, let's say you are driving at 25 meters per second. which if you convert it comes around 30 kilometers per hour or something like this. Maybe I'm wrong, but yeah, more or less like that, or maybe 20 kilometers per hour or something like this. So it doesn't give you any direction. So that's why we call it speed meter. So whenever we see, whatever we see in the car, how fast we are going, actually that is your speed. But whenever we add, let's say you are going at 25 meters per second, but due north means I am telling you the direction of your speed, means direction of your propagation, or direction of your displacement, or your pathway, then it becomes a vector. The vector can actually represent in many different ways, but for the notations it is always have to be block in the block letters, and there can be or be without an overlining on top of that. So you need to learn about the vector. When something is representing like this, you have to understand this is vector, and if it's like this, something is still V in italic, and non-bold one, a normal one, is in scalar quantity. So the vector quantity, let's say we're talking about velocity or speed. If it's a velocity, then the same, this magnitude and this magnitude is the same, but we're telling that this car is going due north. Or we can say that it's going northwest, means in between north and west. Or we can say 45 or 59 degree 59 degree northwest, means from north to west side is 59 degrees. So these have two values, so 25 meters per second and also some directions. So this is a complete example of how the vector representation should be. And speed, as well as speed, is very simple. It just have a value which we call it magnitude. So the magnitude is here only, and here we have magnitude and we have a direction. So I hope the vector and scalar quantities will be easy for you to understand. Now we go for the mathematical representation of vectors. How in mathematics actually we represent our vectors. Basically, we represent our vectors. So far actually I don't know how much you learned about the 3D representation of a vector, but for sure in your SPM or STPM or in your diplomas maybe you learn about 2D geometries. So along x-axis and y-axis, where this x-axis actually here, and then y-axis we use here, right, last time. So there is no axis like this. However, in this course we will always analyze something with regard to 3 different axes all the time. So there is no 2D geometry anymore. There will be always 3D geometry. So a vector representation such as, let's say, velocity and something like this. Let's say the velocity later on we'll represent that one, but let's say there is a quantity which is E, which is a vector, since these are bold, which is a vector. And then a vector, no matter what direction they are going, actually they will always have a direction of 3 different components. Means let's say somebody is heading towards this one, so that one will not have any component on Z direction and X direction, but still this will be 0 and this will be 0, but still will have a direction towards Y. Let's say it's going in between somewhere, so it will have a X component, Y component and Z component. So the total component, the total value of that vector will be actually the summation means the addition and the mathematical addition of the x component means the component towards x direction, a component towards the y direction, and the last component towards the z direction. So whenever we're going to calculate any vector quantities, the value will be there for sure, but the direction is most important, because all the vector quantities will have three different components, because we have a 3D three different axes here. So x direction will have one component, y direction will have another component, and z direction will have another component. So this is how we actually represent any vector quantity in 3D geometry. So also this actually we call it position vector, means like that based on x, y, and z axis, what is the position of that element or that vector or that quantity or that particular value or particular what we call it, velocity or particular pressure or something like this. So you have to always think about that there will be three components: x components, y components, and z component. The resultant component of them together will be the final component of the any quantity. So we move forward from here. So we learned about the position vectors. Now there is since we know already about this, but there is one thing we know, that we need to derive a way of learning the direction also. So we can each what we call vector components have its direction, and also it have its value, because they are all actually vector quantity. So here there is a term we need to know about, which is called unit vectors. Now, how we define a unit vector is a vector which has both magnitude as well as direction, but the vector have to be always have one value of 1, means it cannot have 1.2, 1.11 or 2.3. no, it always need to have a value of 1. Let's say that we have a vector quantity of ex or something like this, right? Let's say we want to find a unit vector along a x-axis, because ex is the component of e along x direction. So here ex here, sorry, so the unit vector comes with the ex, means the vector of the x component of the e vector divided by the magnitude of that same vector, which is we call sometimes a cap. The denotation we call it e cap. So from here we get this one, which is ex vector is equal to magnitude of ex vector and multiplied by a unit vector along that axis. It means that if we multiply a magnitude, means the normal value, any magnitude value, with an unit vector, we get the vector along that axis, or this axis, or this axis. So to represent any vector along any axis, we need to declare a vector. We need to find out the unit vector and the magnitude of that component value. So here we see these three values. So as we replace here ex, ey, and ez, here we get these values. So the new equation becomes ex ax plus EY AY and plus EZ AZ. Now basically it's nothing, don't get so scary. These AX, AY, AZ actually you know already. This is I. So I means AX, means the unit vector along x-axis, which is I. J is a vector which is along the y-axis, which is a unit vector. So J is a unit vector along the y-axis, and K is the same unit vector with the along the z-axis. So, and let's say that the vector component value, x component value, the magnitude of that x component is 3. Sorry, I think I made a mistake here. Should be y here. Should be z here. Okay. So if these three different values have, let's say 3, -4 and 10, so we can write that the EX vector, EX here is 3i minus 4j plus 10k. You have many times have used this same notations in vector algebra, so I believe that now you can actually connect them between what is an unit vector, and what are the values of the x, y and z component. So these are as simple as that. E is equal to 3i minus 4j plus 10k, which is I is the unit vector along x-axis, j is along y-axis, and k is another unit vector along z-axis with their significant values. So now we learn how to write down. By the way, this is a position vector still, because we convert this position vector into this one. So now we know that what is the position vector and what is a unit vector. So let's go for now we have the, since we learn about the unit vectors of the x directions, you know, and the components wise representation. Now what will be the unit vector of this? So as we learned about this one, that unit vector is by definition in any direction. The definition, by definition, the unit vector can be that vector divided by the magnitude of that vector. So here, if we want to learn about what is the unit vector along E direction, means of course E have a component along X, Y and Z, but the resultant component is actually E, right? There should be an unit vector along that direction also. So by definition, the E vector, if we divide it by its value, then it becomes a unit vector along the E direction. So how are we gonna find it? We put here the vector itself, and then we divide by the value of the modulus, means the magnitude value of that one. We will learn about this one in the next there will be an example in next slide. We will learn how to do it. So here, let's say unit vector, it's given, let's say a unit vector of twice I plus root over 5j minus 4k is given. So you need to determine the unit vector in the direction of E, means this one, not in the direction of Y, not in the direction of Z, not in the direction of X. Asking you to find this vector, this unit vector. So we will follow this equation where we put this directly, the E vector here, as we have here Ex Ax, Uy Ay, and Ez Az. As I told you that I is Ax, J is Ay, and K is Az. So we have that vector, and then we want to do this operation. Now what is Ex? Ex means 2, and Ey means √5, and Ez means -4. So we have here this one, and then we have this value. So the final unit vector is this one. After we calculate all the values, we get this one. So I hope that you can later on calculate by yourself. Now we move on to another example of unit vector, that the given E is equal to x plus y Ax. Now we don't give x plus y Ax plus 3y plus z square Az. So there is no I, J or K, but it's same thing. But since the given Ax, Ay and Az, so you cannot put I, J, K anymore. However, let's see what they are asking. So E is given in a vector formation. This is what we call the position vector formation, and asking the unit vector in the direction of E at the rectangular coordinate location of 1, 1 and 1. Means the values are given, x, y and z values are given. Means the coordinate 1, 1 and 1. Means x equal to 1, y equal to 1 and z equal to 1 also. So what we're gonna do first, we will find out, as we know already how to calculate the unit vector. We will try to find the unit vector first, and then what we're gonna do, we're gonna put these values instead of x, y and z. Then we'll find out the value at this point of value of the unit vector at this point of E. So we go for the solution now. So Ex is given here, as we know that Ex is this one, Ey is this one, and Ez is z square. So we have here, so we use this one already. Since we cannot move forward from here, so what we do, we put 1, 1 and 1 instead of x, y and z. When we put this one, we have this values. Sometimes they can give you this one like I, J and K, as what we have done so far in our previous slides. So like this, you will be able to calculate the vectors, unit vectors, if the position vectors has been given. We move on now to some vector addition. This law you know already, that if A and B is given, means this A is here, if we bring this here, so A and B have the same direction, and the opposite direction will be A plus B. And similarly, if A and B is the same direction, then the opposite direction of the parallelogram will be the diagonal length of the what do you call it, the parallelogram will be the addition of these two. So this and this, remember one thing, A and B have to be in the same direction, they're going in the same direction. And then this, if this is the opposite direction, then this will be equal to this plus this. Similarly, in a vector representation, if A, B and C is the same, look at here, A, B and C same direction, then inside this cube A, B and C will be equal to A, B, A plus B plus C. These basic things are actually known to you, but you know, I'm just reconnecting back with this. In similar way, if A and B, they are not actually in the same direction, seems like they are going opposite way, so the connecting line between them will be the subtraction of A and B. So this is also known to you, so I will not go so deep inside these things. And then some like multiplication you can do in a very scalar way, like the normal way, like a, if you multiply, then you multiply with both. You know these things already, but I just want to reconnect, that's all. There is an example here about the implementation and application of the vector addition, subtraction, something like this. So let's say try to solve this, and you will learn how actually this vector addition, subtraction actually works here. So the example is an aeroplane with a ground speed of 350 kilometers per hour heading due west. Means it's a vector quantity and telling that this is due west. Okay, no problem. And it flies in the wind blowing to a northwest at 40 kilometers per hour. So we need to find out the airspeed and the heading of the aeroplane, means in which direction the aeroplane is heading. Okay, based on this data, we have drawn this this diagram to trace their paths, which path they are actually flying. So let's extract from here first. So the ground speed of an aeroplane is 350 kilometers per hour heading due west, right? So if this is north, then this is east, so this becomes west. Okay, so now we know Vg equal to 350 kilometer per hour, but that is the value, means the magnitude, but we still don't know what is the direction of that, right? Since we know that if it's 3D, then it's a different issue, but since we know that there is no 3D here, it's a 2D diagram here, so there is no Z component here, only Y and X. So from here we can see that there is no X component because it's going opposite, right? So it means the direction should be a negative direction or something like this, but we will see when we go to our solution. So our magnitude is here, so Vg is here, and then there should be a wind blowing, right? So wind blowing like this, so it's try to hit this aeroplane. So instead of going straight, due to the wind, it will never go straight, so it will try to tilt towards, little bit towards the wind blowing, right? So it means that wind is coming from here and it's hitting this aeroplane, and due to the wind, supposed to be here showing, and then this one, and with this one it becomes a parallelogram. So here we put this one here, so wind represents actually this one. So due to these two, there will be a resultant direction and will be a resultant velocity of this aeroplane. So we will neither have 350 nor we will have 40. We will have something in between, or maybe more, we don't know actually, because sometimes when the wind comes, it aids you, and sometimes wind comes from the opposite side and actually negates your speed. So let's go to our solution here. In this solution we see that the Vg here is 350, but the direction is opposite, so we have opposite direction of, supposed to be x direction, since it's minus x, but the vector, the unit vector is the same because ax is the unit vector at x direction. So we'll have this one here, and then the same, since it's only in x direction, not in between of x and y, so it doesn't have any y component because it's sine 0, because with y component is always sine, right? So sine will be 0, so sine 0 means 0, and multiplied with it, it will nullify the component which is in y direction. So Vg which have a 350 kilometer per hour and heading west, means negative of x direction, because this is x direction, so we have a minus 350 x. Now this one, the wind, since it's northwest, means it have same angle, it is flowing in between y and x, right? So it means these have 45 degree and it have 45 degree with this one. So it means these have both component, y component and x component. So as we know that the x component, it's going opposite of x, so we have a x component. We know that x component is cos 45 because the angle is 45, so we have cos 45 and the direction is minus x, and then we have the same, the magnitude is 40, we know that magnitude is 40, so the 40 kilometer per hour, so 40 kilometer per hour cos 45, and the direction is minus x. And for y, since it's going up, if it's would have been gone down, it should have been minus also, but since it's going up towards y, it means this ay is plus, so 40 sine 45 again, because it have 45 and this is also 45 because it's in between, totally in the middle of x and y. So that's how we determining now that the wind effect of the velocity of the wind here. Now the addition of these two components will give us the average aeroplane true air speed. So we will just add here, so VA is equal to VG plus VW, and then we calculate this one and we get this one. Now from here, this is a vector quantity, right? So from vector quantity we can have two different things. One is what is the ground speed, means the value of this vector quantity will give us the kilometers per hour, that what we have done here. So the magnitude give us around 380 kilometers per hour, which is actually higher than 350. See, so the wind is aiding actually the aeroplane. And if we find a theta means tan inverse actually y by x. See, this is y, right? The y component divided by x component. So y divided by x component, if we divide it, then it's 4.28 northwest, means what? Here. So northwest here. So that's how you're gonna determine here your direction and then the true velocity of your aeroplane. So this is solved. In the exam, possibly this will not directly come like this. If it comes, some criteria of question comes like this, then the values will be changed, and then basically your understanding, based on your understanding, you can solve it. So you need to understand this rather than you need to memorize. So I will stop now and I will start a new video, and we will discuss the dot and scalar product on that video, inshallah. So assalamu alaikum wa rahmatullahi wa barakatuh.